It goes back to Calc 1, where we're really trying to get at the idea of, all right, what is the extreme value, highest and lowest value on the local level, and what is it on the global level, right? And more importantly, I think, what's the, under what circumstances do you look for one and when do you look for the other contextually? But then kind of a sidebar to that would be the case where, sometimes the local max is the global max. And how do we make that determination? All right. So you look at this diagram here, and it's kind of hard to tell, but if this is a segment of a quadric function, something like a paraboloid or something along those lines, it could be the case that this has a natural minimum over an infinite domain. But what this little boxed out area is doing is actually creating a restriction upon that domain. All right. So I'm saying, okay, you have this entire function that can go on infinitely in all directions, or whatever appropriate directions there are. But what I'm saying is, let's only focus on the areas that are bounded over this rectangle. Okay, so just going from here over, following the curve to here, and then going back the other way, stopping here on those corners. So you have these natural boundaries based off of those restrictions in the XY plane. All right. So I'm really just focusing on, in this interval, what's the highest and lowest Z? And at what X and Y values do they occur? All right. So, the general question, or the structuring of the question, is almost always going to be find/investigate the critical points. All right. But now you can see here there is a restriction to the domain and range. All right. Now, force of habit, I just said domain and range. I was incorrect. What I meant to say was domain. The Y is no longer related to the range. The range is now the Z, because the range is specifically related to the dependent variable. Here we have two independent variables, X and Y, where Z is the dependent variable. She's going to kill you. Not literally, folks. Not literally. No, it's not. It's not going to happen. We're not that bad, but there are consequences in the McCann household when somebody does not study for an assessment. Right? Anyway, so the domain and range are X, and the domain is X, Y. The range is Z. And so what we need to do is keep that in mind, but also try to determine what the most appropriate range would be corresponding with these two elements of the domain. All right. So how do we do that? Well, the same way we do everything else in calculus. Take the derivative, set it equal to 0, and solve. I mean, I'm being facetious, kind of, but there's also truth to what I'm saying. So we would find f sub x, which would be equal to 2x minus 2, f sub y, which would be equal to 2y minus 6, set them equal to 0. So if you set them equal to 0, in the first case, you get x equals 1. In the second case, you get y equals 3. All right. So we need it to be the case that f sub x is equal to 0 and f sub y is equal to 0, which is really the same as saying f sub x is equal to f sub y is equal to 0. Okay, these all mean the same thing. All right, and so there's no reason to think that that isn't true, but there's no way to verify it. because there's no X in this model and there's no Y in that model, right? So we just go with what we have, right? So our critical values, 1, 3, or critical value of 1, 3 is only part of the I was going to say part of the puzzle here, part of the equation, part of the solution, part of the whatever. We also have the bounds to be concerned with because we're looking for, oh, you know what? Now that I think about it, there is a flaw in the way the question is structured. Find the absolute extrema of the function. Yeah. Because the way it was originally structured, it would, once we drew a conclusion about the critical value, we would be done, and that may or may not even have any allow for any relevance to the domain. I mean, so yeah, I knew there was something off about it. Just couldn't put my finger on what it was. Anyway, so we could draw a conclusion about the critical values, critical value in this case, but that doesn't tell us everything that we need to know. But it's somewhere to start. So second derivatives test wouldn't be difficult in this case. So we could dive into that. So f sub xx, f sub yy, f sub xy. So 2, 2, and it looks like a big old goose egg here. So I can get my discriminant. 2 times 2 minus 0 squared, which is 4. So d is positive, and f sub xx is positive. So we're dealing with a local minimum at 1, 3, comma, and I'll write it as f of 1, comma 3. Right. So it's a local minimum, but I don't know if it's an absolute minimum. Right. It looks like it probably is. You know, as it plays out, it looks like, I mean, just looking at the structure of the curve, it looks like a curve. The surface, it looks like it probably is. I mean, I'm not going to be unrealistic and think that you're not going to look at something like Geogebra to get a quick sense of what the graph is all about. So there's nothing wrong with that. You know, I could just do a quick z equals, and really the whole point behind doing it this way is to just get a quick look at the orientation. Because if I can use the graph to help me draw a quick mini conclusion, it takes something off the plate, and that's a good thing. Like I said, I'm not going to be unrealistic and expect that you're going to do every little thing by hand. I need to get that 6 in there, and it's the 6 along the way. And also, to be perfectly frank, can I still be guard? Would be cool. I would never want you to do everything by hand because honestly, I keep saying that. It would require me to grade all of that work. And Lord knows I don't want any part of that. All right, so this is what, aside from just a quick perspective drawing, like, all right, that happened, I suppose. So aside from that quick little fragment of the graph that you see on paper, we have the ability to use GeoGebra, and in GeoGebra, it's pretty clear that there is a minimum. All right, that paraboloid, the circular looking parabola, that definitely has a finite minimum. Now, what we could do is pop in the point, and that would be 1, 3, It's defined as f, so I can write it as f of 1 comma 3. If I can remember to type the f first. One comma 3 comma f of 1 comma 3. I don't know. What am I missing here? I'm going through the whole like, let me keep hitting enter and hope it works. And get into the issue of with GeoGebra second guessing whether I'm typing it incorrectly or if there's something wrong with the way I'm doing it. It looks, I don't see anything wrong with it. I'm going to redefine this as f of x comma y, and if that doesn't work, I'm going to just start plugging and chugging away. Yeah, okay. So I guess that was the secret sauce, but if I type in 1 comma, so define it as f of x comma y first instead of z. Even though it called it f, it should have worked, but whatever. Then 1 comma 3, then the comma f of 1 comma 3. So it figures out that it's 4 for you. But that's not actually why I did that. I didn't do it so it could do the math for me. I'm perfectly capable of handling the simple computations. I did it for the visual. All right. I wanted to be able to look and see that that point, which is now called point A, is the lowest point on that graph. All right. So just so it kind of looks a little bit better. Okay, yeah, okay. This is just getting out of hand here. All right, a little bit more manageable. Anyway, whatever. So we verified that not only is it a local min, but it does seem to be an absolute minimum. All right, but now I want to get the other absolute, the absolute maximum. See if I can get a hold of that. All right. So the way we handle that is because we've only had the one critical value, is we have to look at the boundaries. Right? The boundaries of the function are based off of this curve here, this one, if it shows up, try to get a little bit better here, this one, and this one. All right, so the outer fringes of the bounded region. Try to make it look halfway decent. All right, and what the highest and lowest points are in terms of g there. And so the way we handle that is by looking at our bounds and not only making a determination of what the corner points are, but what the paths are for each one of those. If that were a rectangular bounded region, at least from the intersection of the surface, then I would say the opposite sides, but they're really not sides. They're opposite curves, I guess, and they're not even necessarily congruent. Right? But what I can do is make some assumptions, kind of like we did when we were finding limits. We would say, let or assume, I'll say let x equal -2 only, let x equal +2 only, let y equal 0 only, let y equal 4 only. All right. But then we can start mixing and matching and say, let x equal -2 and y equal 0. Let x equal -2 and y equal 4. Let x equal 2 and y equal 0. And let x equal 2 and y equal 4. All right. These last 4 things, those are actually really easy. I'm just cording this off here. Because when you're letting x and y both be constant, then you're basically saying that you want to substitute something in for X, something in for Y, and have GeoGebra in this case just spit out what the Z value is. So what I'll do here is redefine my point as A comma B comma F of A comma B, all right, if it'll let me. And I only say if it'll let me because of the quirkiness of GeoGebra, not because I have any doubt that it should let me. It's just a question of whether it's just going to be as temperamental as it often is. Have I already used A and B? No, okay, good. It created sliders, which is what I wanted. That was ideal. All right, so and I'm going to verify that the sliders are going to work for me. So at 1, 3, oh, Jesus H. Christmas. Oh, there we go. So 1, 3 gives me a 4. So that's verified, which is good. All right, let me just slide this over a little bit. Maybe I have a little bit more luck with the slider. Oh yeah, this is going to be beautiful. I can already tell. Yeah. Oh yeah, doing great. So -2, 0. Gives me a 22. -2, 4. I'm really just guessing here because there's really no indication. I guess I could try to type it in, but it won't even let me do that. 14. That's even entertaining. +2. +2, +4. So I just grab that one, gives me a 6. And then +2, 0 is what I'm looking for. So let me grab that. Let me again. 14. All right. So I'm looking for the absolute max on this interval. I already know that 14 and 6 are out because I got numbers that are better than that. Right. So far, 22 is the winner for the maximum and 4 is the winner for the minimum. But I'm not ready to draw any kind of serious conclusions here. So until I get into these guys over here, I need to tackle these first. All right. And these we're going to do using a by hand approach. One, because I think I'm going to lose my mind if I have to use GeoGebra anymore tonight. And then 2, it's actually not too bad to do it by hand. Right. So what we would do is go back to our original function we have here and replace the x with a -2. And so it's no longer going to be f of x comma y because I'm making x constant. It'll now be a function of y. -2 squared is 4 plus y squared. -2 times -2 is +4 minus 6y plus 14. Clean it up. Y squared minus 6y plus 22. All right, so it's a function of y. So z equals that function of y, all right? Because either way, it's still going to report out a z, but now it's specifically related to y, right? Which is good because now it's down to one variable. So now I can get this swap out of here. And honestly, I shouldn't talk too much crap about GeoGebra because it is free. and it works for a lot of what we need to do, so that's fine. Okay. What I want to do is I want to find the minimum or maximum related to this. So the highest or lowest point for the vertex for this function. Okay, so z equals y squared minus 6y plus 22. What I'm going to do is I'll write it in as y equals x squared minus 6x plus 22. And with Desmos, I mean, it's great. Yeah, I mean, you just, the vertex, you just tap on it, right? So vertex 313, right? So again, independent variable y, dependent variable f of y or z, that 13 corresponds to, in this case, the lowest point when x is equal to -2, if we're dealing with an equation that's strictly in terms of y, right? It's an upward facing parabola. So what we did was we kind of decomposed it down into 2 dimensions, specifically the yz dimensions, right? So we're going to do the same thing with a +2, making the +2 the value that we substitute in. Okay, and so computationally, the only thing that serves to do, yeah, when I replace the x with a 2, it's going to make it a -4 along with a +4. So it's going to just change our c value a little bit. So f of y would be equal to, we'll have a 4 plus y squared minus 4 minus 6y plus 14. So z would be equal to y squared, these two would cancel, minus 6y plus 14. All right, so my vertex here, just again, tap 3, 5. We only care about z values here. So all these z values that we're coming up with here, these are our possible candidates when we're talking about absolute max, absolute min. All right. And again, we only have to do this because it's a restricted interval. If we weren't given any kind of restrictions, we'd already be done with this problem, because it's an upward facing paraboloid, which means it has no maximum, right? It never stops increasing, and its minimum would be at 4, but they restricted it, so now we're kind of stuck having to do all this work. Right. So here it's now going to be, when we replace the y's with 0, we're going to get a function of x, which is just x squared minus 2x plus 14. Right. So minus 2x plus 14. Tap on the vertex. Vertex is 113. Again, it's just the y that we care. In this case, it's a y value, but it's, in this case, it's still a z. It's x comma z. All right, and so last but not least, and let me do a little shrinky dink here. Replacing all of my y's with 4s, I'm going to have f of x equals 16 plus y squared. Oh, sorry, I subbed in for the wrong thing. X squared plus 16 minus 2x minus 24 plus 14. All right, so x squared minus 2x looks like a plus 6. 30 minus 24. So 1, 5 would be the vertex. And then it really is just a matter of looking at everything that we have and saying, all right, what's the biggest value we got? What's the littlest value we got? All right. Now, again, just like everything else we do together as a class, this is all strictly dependent on me having not screwed up any of the simple computations. Hopefully that didn't happen, but if that's the case, and we can assume that most, if not all of these numbers are right, and we now know that the absolute minimum is at 4, right? Because that's the smallest z value, and the absolute maximum, the largest number I see here out of all the possible z values appears to be that 22. Okay. And so it's a lot of non-calculusy looking work, because really, if you think about it, the easiest part of this process was finding the first order partials, and even the second order partials were pretty easy. The discriminant, super easy, barely an inconvenience. It wasn't until we had to actually evaluate the boundaries that's when things started getting a little hairy. So, you know, it stinks, but that's part of the process. Right. So the last thing I wanted to do tonight is a quick